For many thousands of years, ceremonies have taken place on this country. Ceremonies that would welcome people to the country. Corroborees and ceremonies to celebrate the dreaming. In Aboriginal culture, country is more than just a word or a place. It's a feeling. It describes the entirety of the ancestral domains and holds the stories that continue to be told by the traditional custodians of the land. Stories of significance that have been passed down through the generations of Aboriginal people. Stories that continue to be shared to remind us of the rich Aboriginal culture that surrounds us. A better understanding and respect for Aboriginal culture develops an enriched appreciation of Australia's cultural heritage and is essential to the maturity of Australia and is fundamental to the development of an Australian identity. We would like to acknowledge the country and the traditional custodians of the land on which we are meeting today. We pay respect to the elders, past, present and emerging, who guide our spiritual and learning journey, and extend that respect to all other Aboriginal and Torres Strait Islander people with us today.
Good morning, everybody, and welcome to the third in our webinar series on the topic of Beyond the Basic AV Network. This webinar series is brought to you by the 5 cable registrars across Australia, which is ASIL, ACRS, BRCA, TITAB, and FPA. And a special thank you to the FPA and to Julia Bearclough for providing this webinar software on which we're sharing this information today. The 5 registrars and ourselves, the International Copper Association, of which I'm the CEO, all came together to support your businesses through the Registered Cabler website. I'm sure most of you are aware of this effort. I would encourage you to go to the website and have a look at it after this seminar and look at the opportunities it might present to your business. Some administrative notes just before we start. Your microphones have already been turned off automatically by the webinar software, but we welcome your questions or comments. And in the top right-hand part of your screen, you'll see a Q&A and a chat box there. So please just throughout Andrew Sherar's presentation, just put in your questions and we will come back to those at the end of this session. We'll run for 35 to 40 minutes with the session, and then we'll come back to Q&A. So let me now introduce your presenter, Andrew Sherar. He's been in this industry for a long time. He's got 35 years of delivering architectural lighting solutions. He's had a bachelor degree in electrical and electronic engineering. He's a technical director of Lightmoves and Resolution X. He's got extensive history in live production technology. He's got 10 years of dimmer design and manufacture, and he's certified with Philips Dynalite, KNX, Jace, Tritium, Harman Kardon, QSC, and AMX certified. So Andrew is a true expert in this field. So we wish you the best. This is an introductory session to give you a good flavor of the opportunities in AV networking. So without any further ado, I hope you enjoy this session, and over to Andrew Sherar. Andrew?
Thanks, John. Thanks for those kind words. Yes, I certainly have had quite a bit of extensive experience over the years, deploying many projects throughout Australia, and hopefully I can share some of those experiences with you today, and hopefully give you a little bit of an overview of a lot of the emerging AV over IP type systems that are coming to market. So basically, we'll start off with a bit of an overview of the topics that we're going to cover today. So some of the basics are obviously IP communications and what we sort of modern day sort of topology of what we need to do. We then go to sort of applications and protocols. So we'll try and share some real world examples with you to give you a bit of an overview. We'll get into some of the nuts and bolts, particularly with what's happening with video streaming and different compression routines. And then obviously we'll finish up with some Q&A. It's a fairly complex topic that we're discussing. So at any point in time, please jump in with Q&As as I cover the material, and hopefully I can answer those subjects for you at the end. So if we go to IP communications and basics, all of us have had a lot of experience these days of browsing the internet. A lot of us probably don't understand what's happening below the surface and the communications that's going on. So some of our most basic communications over the internet, if we're sending and receiving emails or browsing the internet as far as web pages, we're generally using TCP/IP communications. So this is basically point-to-point communication. So on your computer, you've got your browser going. You basically browse to a web address, and if that web address is valid, it'll respond back with obviously the relevant content of that web page. If it can't find it, it'll come back with a 404 response and can't find it. And this is the basis of TCP/IP, in that basically when we send a request, we get an answer back straight away to let us know that the message we're requesting has got to the destination, and basically it's answering back to the source to say, yep, got that message, and here's the relevant information. So really, really good for point-to-point communications. And effectively, it's like two people talking on mobile phones. Effectively, you're interacting with each other all the time. You know exactly what's going on. Unfortunately, it's not the greatest communication protocol for IP streaming because there is a lot of overhead in doing that. So for real-world applications and particularly live broadcast, there tends to be a fair bit of latency involved in using TCP. So that's when we tend to go to UDP, which is User Datagram Protocol. So effectively, it still sits on Internet Protocol, but it's a different packaging methodology in the way that it communicates with the target devices. So in our simplest format, we've got UDP IP broadcast. So this, in a lot of instances now, is being basically firewalled out on a lot of networks because it tends to flood the network with lots of messages. And basically every device that's on a single network receives that and decides if it needs that data or throws it away. As a result, it tends to flood networks, and so not highly desirable, particularly via network engineers. So in most cases, we find alternatives. A simple analogy of broadcast is basically like me talking to you guys. Hopefully you all getting what I'm talking about, but there's no answer back. I don't discover that every person's actually receiving this message. When we go to UDP unicast, it's very, very similar to TCP/IP, but there's no feedback effectively. I basically send a single message to a device and hope it gets it. So there's no guarantee that the receiving device gets a message, and there's certainly no answer back. So it tends to get used a little bit in some streaming applications. The main one is what we call UDP multicast. This sets up some dedicated IP addresses on a network that basically become like a meeting place or a meeting room. So effectively, a transmitter will basically transmit out to a single IP address, and then a single receiver or multiple receivers can all log into that IP address and receive that data. This is typically what's used in sporting stadiums and so forth with IPTV. So it effectively gives us multiple meeting rooms we can use just by different multicast IP addresses, and certainly something you can research in your own time. There's a lot of information out on the web about it, but effectively each IP address becomes a single meeting room, and simply we can select different broadcasts just by changing the IP address of the receiving device of what it's logged into. If we start going through applications and protocols, common AV applications. So we're all used to the likes of Stan and Netflix in this day and age, where we're basically live streaming, or sorry, not live streaming, but basically streaming content from Netflix and other providers. In these cases, in most instances, they're actually using TCP/IP. There's a good reason for that, because our receiving devices want to be able to analyze the bandwidth of the internet that we're actually getting to basically receive those packets. So effectively, when we get content via Netflix, doesn't matter if there's a 5-second or a 10-second or 15-second delay, because effectively all the content's pre-recorded. All we're doing is playing back typically movies or TV series that we desire to watch. So in those applications, any latency or delay in broadcast doesn't matter. Typically, our receiving devices will basically receive the TCP IP packets and cache them or store them away in our device. So if we start getting dropout on the internet or our bandwidth drops off, basically it will automatically scale back the resolution of our receiving device to match the bandwidth of the incoming data. So good example of that is particularly in Australia with the NBN. Many of us know that in the peak periods of probably 6 o'clock at night through to about 10 o'clock at night, when there's lots of kids on the internet gaming, lots of people streaming media, that our overall bandwidth can drop back quite considerably. And typically, rather than getting something in high definition when we're trying to stream material, it'll actually drop back and you start getting pixelization or blurring of the image. And this is typically because of the bandwidth reduction in our internet capability. So that's a fairly good live example of what sort of goes on in the background. So obviously pros, it does use that TCP IP to establish the connection capability. And obviously the look-ahead cache shows storing of that material in your device, in its memory. So if the internet does drop off a little bit, we're not getting dropouts, instantaneous dropouts in the content that we're viewing. But yeah, the quality is very much dependent upon your internet bandwidth. Typically, if you've got multiple devices in a residential application that are all trying to stream Netflix or other content at the same time, you're going to want probably a minimum of 50 megabit download capability to be able to do it. So the other common AV application, it's probably one we've all seen, is IPTV. So this is the one that uses UDP multicast. So typically if we go to something like a sporting stadium, if we go to somewhere like MCG, for instance, and we see all around the stadium, there's lots of bars and monitors around the concourse that are all showing the live broadcast of what's going on in the field of play. So in those instances, what's actually happening is we've got the broadcasters are doing a video feed back to the main control room within the stadium. Within that stadium complex, there's a high-spec encoder that's encoding that data in real time. It's pumping it out across the network via multicast. And then all the receiving devices all have a local decoder that's basically then decoding that multicast stream and then basically normally transmitting it out via HDMI to a local monitor or TV type application. So that's real world application. And in those instances, it's all about the latency. You can't have any delay, obviously, in what's happening on the field of play because you've obviously got an A/B comparison to what's going on in the field of play versus what's going on in the monitors. So hence why they use very high quality encoders. They are quite expensive, but in comparison to where they were probably 5 or 6 years ago, quite affordable in comparison. So some of the things we see, obviously in live performance space, is basically audio over IP. So there's a couple of different ways of doing this. Here's a typical diagram showing some of the typical ways of how we can transport audio over IP. So again, in live performance, mixing consoles these days, everything is basically over IP. So if we go to something like Carols by Candlelight, there'll basically be something like a front of house console that's receiving IP data from stage boxes that are sitting on stage that all the microphones are directly plugged into. That's basically converted to IP streams, set up to the audio console, also sent to a secondary console on the side of stage, known as a fallback console, that controls the on-stage speakers and so forth. A lot of the amplifiers these days, rather than having direct analog inputs, are now directly have direct IP connections. So effectively, we stream audio directly to the amplifiers. So effectively, the last time it leaves the analog domain is from the microphone to the stage box. Everything downstream is digital until it gets to the amplifier, where it's converted back to an analog signal again out to the actual loudspeakers. So that's a sort of common real world example. Here in this diagram here, you can see we've got things like basically a paging microphone that's PoE. Again, this is a great typical example of how we can deploy networks in this sort of environment using power over Ethernet. We can basically power the desktop microphone. It's basically converting that to an IP stream and sending it over the network. And then we're basically routing it to where it ever needs to go via other methodology. Likewise, if we look at a typical video network, we can see here where we've got effectively some content going into an encoder. It's going out to an IP network and then going out to various devices around. So whether it be a video wall, local monitors, it doesn't matter. Effectively, it's all basically using the IP as a way of transport. So we'll basically get back into some of the protocols. So looking back over the audio side of things, there's two main protocols that are used out in the marketplace. There's AES 67 and Dante. Dante is my particular favorite because the technology was invented here in Australia and now basically is the go-to in all professional audio worldwide. So if you go and buy a brand new Yamaha mixing console, for instance, and look on the back of it, it'll have effectively a native Dante interface. It'll generally have two network ports on it, so effectively a primary and a secondary, and that's mainly set up for live production where in most applications we run redundant networks. Obviously, the show must go on type mentality, so the network infrastructure is absolutely core to making these systems very, very robust, hence why we have a primary and secondary interface. This technology, there was other alternative technologies before Dante. There's quite a few called CobraNet and other methods that were around the world. Most of them are fairly expensive to deploy and needed dedicated networks to do it. The beauty of Dante is it can sit on top of any type of standard network. Typically, the Dante network itself would be VLAN off or virtual local area network, where we can set up effectively a dedicated virtual network on a physical network that has all the audio data on it, and we can dial up the quality of service on that network to ensure that the data gets through. The best part about it is that the software to configure it and do all the routing is basically a free download from the website. There's a link at the end of this presentation if you want to go and do further reading on it. But yeah, we're now seeing in some applications now Dante-enabled ceiling speakers. So in the old world of doing things, we used to use a 100-volt line, which is basically a double insulated cable going out to speakers to do all our typical foyer systems and so forth. Now you can basically run a network cable. It has a built-in amplifier, runs on PoE, and effectively we can send audio up to that loudspeaker digitally, and effectively it can do all the processing and decoding locally at that speaker. And the beauty of it is that, particularly in a foyer space where we've got ceiling speakers at different levels, we can now tune those speakers to be at the right audio levels to get consistency over the target audience. So obviously highly desirable, a lot better than the old 100-volt line system where we used to have to do different transformer tappings to try and get the right audio levels. So obviously one of the cons, I suppose, of Dante is that it does need licensing on a per device basis. Audinate were very clever when they first released this and basically insisted that everybody had an extra chip in their network interfaces to do this. So effectively the licensing was done by a hardware chip in the actual devices. And so effectively you went and bought a Yamaha console or a Dante-enabled amplifier, the chip would already be in that device, and effectively you're paying for it when you procure that device in the first place. We're now seeing certainly lots of Dante-enabled software devices, so particularly digital signal processors that are used out in the marketplace. So brands like QSC, for instance, if we do Dante on those now, you have to buy a software license, and that gives you a certain number of inputs and outputs that you can do. Typically 64 inputs, 64 outputs. And within the digital signal processor, it basically replaces racks of old analog gear like graphic equalizers, compressors, limiters, and crossovers that are typically used in large-scale audio systems. So it does give us a lot of flexibility and capability. And the beauty of doing everything in digital world is that we're not introducing analog noise like we used to back 30 years ago. I remember when I first looked at a lot of rock and roll touring systems back when I first started in this industry, and you'd have racks and racks of gear, and every piece of gear would add analog noise into the system. These days, everything's just dead quiet because it's all in the digital domain. So the last time we see it leaving analog, as I said earlier, is when we plug a microphone into a stage box, and it's effectively converting the analog to a digital bit stream at that point in time. So from now on, everything else is digital downstream. The byproduct, I suppose, is in the analog world, everything was instantaneous. So when you spoke into the microphone, it instantly came out the speakers. These days, the big consideration is with all the digital signal processing that goes on. So whether it's the console itself, the downstream processors, or the end amplifiers, all of those devices add latency to the signal. So obviously, as that builds up, it adds delay. And most of us can well appreciate delay. If you go to a large stadium and go to a rock concert, if you're sitting in the nosebleeds back in the grandstand, you obviously see the performer on stage and they're singing, but when you actually hear it, it's sometime later because you're so far away from the speakers. And that's just because of the speed of sound being quite slow. But obviously, as we increase our digital systems, if we don't use good quality gear, that gets exaggerated by the digital signal processing as well. The other one, AES 67, it's basically worldwide standard. It's free to use. The only drawback, I suppose, with AES 67 is that if you do use configuration software, you generally have to license the actual software. It's not a free download, but the application itself is free to use and fairly well covered by, again, a lot of the digital signal processing organizations. QSC, for instance, cover both AES 67 natively within their amplifiers and digital signal processors, but also have Dante there that can be licensed for obviously connection to consoles and other devices. Okay, probably go back in I suppose, in a little bit of history here and start talking about video over IP. Before we get to that, obviously, we've got to talk about our sort of legacy type systems. And so when we normally connect a computer or a DVD player to a domestic television, we're using HDMI cables. It's a great transport. It has its origins from DVI interface from computers back some years ago. And effectively, it's digital RGB data, H&V sync out to the monitor, and digital audio that goes out to the TV set. So one cable connectivity, it's absolutely fantastic. The big drawback, obviously, is that we can't go any greater than 5 meters unless we use high-quality cables. And even then, the limitation is probably around about 20 meters. Anything beyond that, because effectively it's single conductor on each of the RGB formats, we tend to get too much slewing on the cable, and therefore we start getting dropouts or digital distortion of the image, or in some cases it just won't display it at all. So if we need to go any more than those sort of distances, we have to look at alternative technologies. The other thing is it only does cover the video and audio side of things. There's no control format down the HDMI cable whatsoever. So whilst it will feed back the resolution of the display, that's about as much information it gives you. It doesn't give you the ability to change sources or turn the device on and off. Probably an extension to HDMI is what we call HD-Base-T. So this is where it does use standard Category 6 or Category 6A cable. in most applications for HD-based-T, category 6A should be the absolute minimum that's utilised, mainly because of the potential bandwidth that could be utilised. So with HD-based-T, we can now go up to 100 metres, so it falls within our normal cabling rules, effectively from our transmitting device, which is normally our HD-based-T encoder, which has HDMI or in broadcast capabilities, SDI inputs on it, audio inputs, and obviously some sort of interface for control. And we can basically plug a single conductor into a projector or a monitor and basically get audio and video up to that device. And more importantly, we can also control it very simply in the background as well. So in AV integration type applications, this tends to get used quite a bit. What we do see in the marketplace as well is there are dedicated HD-based-T routers. So effectively, you can have multiple inputs coming into a router that's then got a whole lot of RJ45s on the outputs, each one being a switchable output, but it's a direct point-to-point link to projectors or monitors. So a typical application might be a large lecture theatre where you might have a main screen in the middle, a couple of side screens, so 3 dedicated lines for HD-based-T going back to a router, and the main presenter's material might be on the main screen and then supporting documentation going on the alternate screens. So that's that sort of real-world application. The big problem with it, even though it uses RJ45 and standard category 6A cable as a transport, it's not an IP protocol, so we can't go via normal generic networks. So an extension upon that, and this is something we're seeing a lot more of these days, is NDI, or Network Device Interface. This typically gets utilized more and more where effectively all the devices are encoding video and audio streams into IP streams, and this can now go out across our standard generic type IP networks. So this is a typical diagram of what this sort of actually looks like. In our simplest formats that we're probably well used to is CCTV using webcams. Uses slightly different because it uses what's called RSTP streams, which is very much dedicated in the CCTV type applications. Once we get out into real world quality type content, so we've got good quality cameras, good quality audio, we tend to use this NDI a lot more. So here it shows a typical sort of PoE network switch, a couple of PoE cameras which have local audio plugged into them. So these cameras are converting effectively to our IP streams into a PoE switch for distribution and then going out to the various devices. You can see that we've also got camera control going back in. So typically in this sort of application, we can do our normal PTZ type control of the cameras. And we can also then via IP control the various devices of what they're actually receiving. So in this case, we've got 3 transmitters being our 3 cameras. And obviously we can control, these might go to multicast type streams, and then we control our receiving devices as to which multicast stream they're actually logged into. So effectively, this is where it gets our typical sort of IP routing type applications. Okay, getting into some of the nuts and bolts of it. So the big thing, obviously, once we do video over IP, there's a lot of data. In fact, video is probably the biggest burden on any typical network, far more than anything else. So we've seen for a long time there's various compression routines. So typically when we run Zoom or Teams meetings, something we came used to very well during the pandemic a few years ago, there's a lot of compression that goes on in the background using MP4. So obviously, if we look at typical broadcast type video and we start broadcasting this out in typical data rates, this chart on this page shows you some of the typical data rates we may see if we used uncompressed data. So if we go to one of the really emerging resolutions, which is 8K TVs, most of them have probably heard about them at Harvey Norman or JB Hi-Fi. Very little content available for them yet, but it's certainly the way of the future. 8K is probably the closest thing you'll ever see to film in resolution. It's very, very high quality. But when we start looking at our bit rates when it's uncompressed, you can see on the bottom right there, it's 35 gigabit on a network. You'll be hard up finding a switch that can handle probably 2 of those streams because of the backplane speeds of a typical switch, let alone our cabling and fiber topology that's going to cope with that. So as a result of that, we really, really have to compress our streams accordingly. So that's when we start getting into compression. So if we have a look, typically one of the big things that's been used for many years is JPEG 2000. Typically gives us compression rates of 20:1. This one is a really great little chart because it actually shows you typical sort of fiber or cable capabilities depending upon what you want to do. So our normal TVs that we have at home are generally what we could call HD or 1080p. So effectively, that's giving us our 10,080 pixel typical horizontal resolution, and basically giving us fairly good quality television, certainly a lot better than the old analog days. Obviously, once we go up from there, we've got the 4K broadcasts that are starting to happen. And obviously, there's quite a few Foxtel channels that now offer that as a capability. And then up from that, we go to 8K. So we can see typically, again, on the left-hand side, we've got our uncompressed data rate. So even our HD as an IP stream on normal networks, almost 5 gigabits. So extraordinarily high. When we see that we go to JPEG 2000 compression on a HD signal, all of a sudden we're down to 0.22 of a gigabit or 220 megabits per second. So easily capable on normal Cat5e, Cat6 type infrastructure. And that's what we're all probably used to using. So effectively, this is what's happening again with your typical Netflix and type application. So effectively, it's coming in as compressed bit streams, and then your device, whether it's a television or an iPad or an Android device, it's basically decoding and those compressed streams out to the video side. So in some cases, it's done by hardware decoders. In most cases, particularly with devices, it's done in software as part of the operating system. So again, when we have a look at some of our typical applications, we see here on the left-hand side, this is a traditional AV system where we've basically got a typical AV sources that are going via HDMI, going over twisted pair type interfaces. So this is non-IP, but just giving us some cable distance, going through to some AV switches, and then out to our field devices. Once we go to an IP-based system, we can see on the right-hand side, the heart of the system is a switcher, but it's actually a standard Ethernet switch. And again, these are going out as typical sort of multicast type streams via multiple encoders. So when we're using typical H.264, 265 compression, these are many devices in the market that do that. We use quite a bit of them in school type applications where we're basically encoding the bit streams down to IP and then distributing it through. So many type classroom applications, particularly in a lot of the large private schools, use these applications on a daily basis. So again, the beauty of it over IP is we've now got basically video, audio, and control, all as part of an IP stream. So we can now control our devices, turn them on and off, and basically switch sources and normally to an IP stream and decode it accordingly. Obviously, if we are looking at older premises, you may have to look at doing some cabling upgrades. One of the big things, obviously, and particularly with you guys being as part of the registered cabling industry, is you do need to look at the cabling infrastructure to allow for the future growth, particularly with video over IP, because as I said, it is one of the biggest consumers of bandwidth. Okay, so one of my typical favorites is obviously sports stadiums. I have a very high involvement in a lot of sports stadiums, particularly around Victoria. So I look after a lot of Melbourne Olympic Parks venues, MCG, Marvel Stadium, and so forth. All of these in the background are now using Cisco certified stadium network design. And as part of that, it's basically a single converged network. So security cameras, all the Wi-Fi points for the patrons to log into, all the IPTV streams, everything is now going on a single network platform. Probably needless to say, they're highly comprehensive in their network engineering and design, and a lot of these stadiums probably have 5 or 6 network engineers on staff at any point in time, mainly because the network is the heart of the whole stadium for all its day-to-day operations. So not only are we talking obviously audio delivery, we're talking the vision, HVAC control, lighting control, everything going over that single network, as well as all their general internet as well. So each of those generic services is normally on its own specific VLAN, but obviously the biggest burden on all of it is the security cameras and obviously the IPTV that goes over those systems. So typically they'll have Cisco switch stacks in various locations with all the TVs basically routed back to that, local decoders on each of those monitors in the bars and concourse, and basically all connect back via the converged network to the main control room, where they've got some very high-end encoders to basically broadcast that around the stadium. And something like the MCG, all the audio is distributed via Dante, effectively via a single control point. That was deployed by a very capable local AV company in Melbourne some years ago. And the audio quality of the MCG now is fantastic as a result, because every single speaker cluster has its own delays and effectively tuning going to it. So it gives really great audio response for all the patrons, far better than what used to be there some years ago. And that's certainly the way it's certainly all gone. In a modern day world, if we go to somewhere like the MCG, we watching a game of AFL, a goal gets kicked, particularly for the home team. The operators upstairs push a single button on a control panel. It's then integrated where it puts out live content to the scoreboards, all the LED ribbons around the stadium to basically show that the goal's been kicked by the home team. It'll typically trigger some lighting effects on all the sports lights. And if they've got any form of thematic or colored lighting, it'll generate effects on those as well. So again, it's there to improve the experience for the patron. But again, everything's reliant on that back-end network. So in all those sort of topologies, all the field cabling is Cat6A in those sort of environments. And certainly all the core infrastructure is all fiber back to some very high-end switches and aggregation switches and firewalls to basically collate and distribute that data accordingly. The big thing to probably note is that typically in those sort of environments, each switch port, you're probably looking at well over $1,000 per switch port, just because of the high level of Cisco switches that are required and all the back end site fiber and firewall requirements. Okay, so nuts and bolts, obviously cabling and fiber. The big thing is obviously any form of new installations should allow for video content over IP in the future. So absolutely crucial that Cat6A or Cat7 is deployed in these newer projects. Certainly in any of the theatres, school theatres and professional entertainment environments I'm involved in, it's all Cat6A as a minimum spec and lots of fibre tie lines. So typically single mode fibre and giving us a high bandwidth capability to look forward to in the future, because obviously we now got a limitation of 8K at the moment, but who knows what the future might bring. I mean, it's only 20 years ago we were watching PEL TV at very poor resolutions, and when you compare that to where we are with 8K flat panel displays now, there's been a big increase in the last 20 years, so who knows where we'll go in the future. Okay, some of the other things obviously of interest, Internet of Things and IoT emerging type applications. The big thing at the moment is obviously there's a lot of wireless stuff going out on the market. The big one is probably Matter, which you'll see a lot of in residential applications. This is basically using low power Wi-Fi and is basically a fully open protocol for smart homes. The big thing is it's the first time that the likes of Apple, Samsung, and Amazon Alexa have all got on the same page to come out with the common platform for control. So no longer have you got the sort of Android versus iOS type argument. You've now got basically a way of basically transporting data over wireless mesh networks in a home. And I would suggest probably in 5 years' time, you'll be able to go to Bunnings or your local supermarket, buy Matter product, go home. It'll auto find all the other devices on that network, and they'll all be able to intercommunicate. The big thing is it is low power Wi-Fi. The data bandwidth is limited. So looking forward, is this going to probably support streaming devices of audio and video? Probably not, but it certainly will give us the capability to control those devices and switch those sort of devices. The big one we're seeing, particularly in commercial environments, is Thread. We've deployed some very big Thread networks already in commercial lighting applications, and we're seeing that more in smart buildings where particularly some of our older buildings, I've done one heritage building where no new cables could be run. So all the legacy light fittings were pulled out and effectively Thread-based wireless devices were replaced, which were basically modern-day LED fixtures with Thread devices. And effectively we did DALI over Thread, which is now called DALI Plus under the DALI certification standard. And it allows for basically wide building control and monitoring and all the other DALI capabilities in old school buildings where we can't run any form of new cabling, and all done on wireless platforms and inherently very robust. Where to find further data? Obviously, if you look at any of these links, these should give you a lot more reading information. Again, this is just an introduction to what some of these technologies are. There's plenty of further reading you can do on this, and expect that if this is a tease that you want to basically look and do some further research, feel free to go through these links and look up further data. So on that basis, I'd like to see if there's any questions that any of you would like to ask.
Well, thank you, Andrew. I thought this was going to be AV basics, but it's definitely a little bit more than basic for me. But thank you very much for your presentation. We've got already some questions up on the Q&A. So perhaps you can just run through. Can you see those, Andrew?
Yes, I can. Yeah, look, I'll certainly run through those. So,
and before you start,
one of the first questions is, how important is the quality of the copper cable for audio? Yeah. Well, obviously in the analog side of it, so from our audio amplifiers out to the speakers, absolutely critical. The hi-fi buffs will probably bone me, but there's a lot of things like very expensive monster cable and stuff that the hi-fi enthusiasts tend to use. At the end of the day, the big thing with audio speakers is it's very low impedance, so you can never have too much copper. Certainly in some of our applications where we're using large power subwoofers, so typically 1,000 watts, we now sell an amplifier that we use quite a bit that's 20 kilowatt amplifier across 4 channels in a 1 rack unit type unit with a 3-phase input. It's absolutely extraordinary. So to give you an idea, it's about half the power in 1 rack unit of what KISS toured here in 1980 for their whole PA.
Wow.
So it sort of does put it in perspective a little bit. And obviously when we're powering those large power speakers, you can never have too much copper. So typically when we're running out to speakers in that sort of environment, short cable runs and typically 10 mil plus, because it's all about minimizing the cable impedance, because the longer the cable or any build up in cable impedance, we just get I squared R losses. So therefore we're not putting all the amplifiers power into the speakers, we're heading the cable instead. Obviously from microphone cables and so forth, very important. They generally use balanced audio lines, but once it goes into the stage box, from there on it's in the digital domain. And so therefore it's just standard category 6, category 6A type cabling in those applications.
Thank you, Rob.
One of the other questions was, can NDI flood the network? Yeah, look, absolutely it can. But again, it's all about how the streams are done. In most cases, because we're using quality encoders, they'll basically compress the data stream and they'll multicast to a certain address. So rather than doing a broadcast flood of a network, it's generally done by multicasting. So whilst it does use up network bandwidth, it's done so in a controlled environment.
Can I just make one comment, if you don't mind, on the copper side? Is that be careful with it's great to use Cat5, Cat6A cable, but make sure that you're actually buying genuine Cat6A cable. I'm sitting in a standards committee with Comms Alliance, and someone's just bought a lot of cable that they tested, in particular patch cords, and they're all rated at Cat6A, and they all failed.
Yeah.
So you bought, so just be careful who your supplier is.
Look, it's a very, very good point. And one of the big things that I see a lot of too, which is probably a bit of a side issue, is the big use now of PoE and PoE plus type applications. So we're now seeing more energy being pushed out via PoE from high power switches to deliver things like audio out to speakers and so forth. The big thing obviously now is we've got typically 1 amp we might be passing down a category 6A cable. So it's all going to be about the cable quality and more importantly the field conductors or terminations that are done. Mm-hmm. So if we value engineer and go for some of the cheaper connectors in the marketplace and we're passing DC current through them, 2 years later you might go to pull it out and just pull out a piece of corroded mess because effectively the dissimilar metals, particularly with DC currents, is a catalyst for galvanic corrosion. So it's something that doesn't get taken into consideration in a lot of cabling environments, but it's a really important point.
And the other thing you also mentioned that obviously we've been able to move away from having 100-volt line speakers, because of the way the IP is deployed, and it's worthwhile noting that if you are installing a speaker system using 100 volts, so technically you have to be not only a registered cabler but a licensed electrician.
Yes, you do. So it's exactly right. So typically 100-volt line speakers, by their very definition, need to be on double insulated cables. You'd be surprised how many times I see them still on old figure 8s, which effectively is an illegal installation, and it also should be on the mains tray, not on comms trays, because it's over SELV. So therefore you'll find typically, and I mean obviously our normal application that we all see day to day is our EVAC speakers as part of the fire systems, with the red cables that are put out. And I still often see them run in standard single insulated figure 8s. That's basically an illegal installation. It's got to be double insulated because it is over the magic 48 volts.
It's actually it's what we call now ES3, energy source 3. So
yeah.
I just wanted to ask you one question that I thought is with Dante. Okay, does Dante manage like the delays, as you said, between the nosebleed, because everyone has to hear everything, not only as though it's happening in the stage, but also all the way up in the nosebleed section. So obviously it manages to ensure that all the speakers are sort of all in phase.
So they're basically the way that's done is via digital signal processing. So when you go to a modern day concert, you'll obviously have your left and right array clusters, and each of those individual speaker elements, typically with 6 degrees on the vertical. So they're all aimed at particular parts of the audience to try and maximize the audio coverage over the audience. You'll then see what's called delay stacks are back typically near the front of house console positions, and they will have a delay, so automatically programmed in there based on the speed of sound. So effectively that way the original audio coming from front of house and the delay stacks all appear to be in sync. So that's done as part of the processing. Typically when I commission any theatre systems, the same thing. If you're running some fill speakers back on the stalls, for instance, in a theatre space, that they'll have a delay typically based on the amount of distance they are from the stage speakers. So unfortunately, you can't beat physics. Speed of sound is 330 meters per second. Speed of light's 3 by 10 to the 8 meters per second. So there's a very, very big difference. So you're always, unfortunately, going to encounter some form of delay. If you're in the nosebleeds, just because of the physics of audio, it is always going to be delayed.
So, Andrew, we've got some questions from Robert, Paul, and Tanya. Do you want to have a look at those?
Yeah, sure. So moving forward, one of the questions here from Rob is basically, question is, how important is it moving forward data cables have a knowledge of basic IP networking? Look, it's not that important from a data cabling perspective, but I think it's actually important for a lot of cabling and electricians moving forward that they do have a better knowledge of IP. It is going to be more and more prevalent over a period of time. I can guarantee that no one could set up their own home Wi-Fi network probably 20 years ago. These days, obviously, you can buy stuff. It almost self-configures itself. But most people are now used to actually typing in some IP addresses and having some really rudimentary knowledge of IP networking. I think that's going to become more and more prevalent because there's obviously a lot more training at secondary school level on that sort of stuff coming out anyway. And I think it's worthwhile that any registered cablers have some form of knowledge and do a little bit of research on it and a bit of reading. And maybe do some courses on basic IP, because certainly in the future, there's going to be more and more smart buildings, both residentially and commercially. We're seeing them here and now. Every project I deploy is pretty much on an ICN or integrated converged network in all the smart buildings. Certainly there's network engineers deploying all that sort of stuff. But obviously, we're seeing electricians stuff having to connect into it. And the more knowledge base they've got, I think it'll certainly put them above and beyond some of their peers.
Right. Thanks, Rob. Thanks, Andrew.
One of the other questions from Paul was, how familiar is the AV industry with ICT infrastructure, with Cat6a, fiber, and Wi-Fi 6? I would say the AV industry is probably one of the most knowledgeable of the lot. Certainly from our perspective and our knowledge base internally and what we provide into the market, we're very, very knowledgeable on it. And certainly a lot of our competitors in the AV space, I would say, are probably some of the cleverest network engineers I've come across, to be honest. And probably a lot of them would run rings around a lot of the guys from some of our larger telcos in their network knowledge and capability. So, yeah, they certainly far exceed the average expectation, and certainly very up with deploying that sort of stuff. To give you an idea, when we do a live-to-air broadcast, we're now one of the sort of major network providers for that. So we'll provide all the network switches at front of house on stage and deployed around the venue for the various receiving devices. We'll generally run token ring fiber around with redundant links. So if a road case gets rolled over a fiber and cuts it in half, it won't matter because of the redundant links we've got in place. We must have the show must go on type mentality. So a lot of our redundancy and network engineering that we do, even on an AV and lighting type production environment, is very, very extensive.
Thanks, Andrew.
If you want, I'll handle the one from Robert. Should it be embedded in IP training into the UEED V008 training unit? I don't know the full details, Robert, of the competency unit, but my only concern is the knowledge is needed. The question is, are we then overloading a particular competency unit? So, but definitely, it's a bit like you have to become an electrician before you can become an electrical contractor, if I can put it that way, and run your business, because you need to have the technical skill. And the question is, should we then do the sort of teach them how to run a business while they're doing the electrical apprenticeship? It's to me, it revolves on what do you do first. So I think the thing is, get your basics, understand cabling and cabling practices, then we build on that. But it's up to individuals to realize that this knowledge is required. But it's worthwhile having the discussion, Robert.
Okay, we've Andrew, I think we've got time for one last question from Ian, and then we'll
So yeah, one of the questions obviously from Ian is Wi-Fi eliminate the need for cabling? Absolutely not. So again, wireless is a good fallback for where you can't run a cable, but in all new installations, and I unfortunately see it coming up from the consulting community a lot at the moment where there's lots of wireless light fitting. So rather than running cabling, they're falling back onto wireless type solutions. We've just deployed probably the world's biggest thread network at 500 Burke Street here in Melbourne, utilizing Dali Plus or Dali Wireless. And in fact, it was a refit of a building, but they basically gutted the building and started again. In my opinion, it should have been wired. It was done wirelessly, but I always say if you can run a cable, run a cable. The problem with wireless, as we all know, it's statistical. And some of us probably have those horror stories of years ago when you used to go to a game at the MCG with 100,000 people there. You couldn't make a phone call or browse the internet or even send a text message, mainly because the amount of devices in one area. What works on wireless today, will it still work on the same wireless frequencies in 5 years? Who knows? There's no guarantee. So if you can run a cable, always run a cable.
Terrific. Thank you, Andrew. And thank you for that excellent presentation. Really wonderful to get a good knowledge of the basic AV networks. And I hope everybody joining us today enjoyed it as much as I did. Thank you, Ian Milner, for helping put this together with the all of the registrars, ASIL, AECRS, BRCA, TITAB, and FPA. And thanks again to Julia, who's been managing this webinar. And it's a wonderful presentation, Andrew. And for all those who would like to ask more questions after this, please, you can go onto the Registered Cablers website and post a question on there, and we'll answer that promptly. I'd also encourage you to have a look at the Registered Cablers website. It's all about helping your business attract more customers in this area. And we promote you by region and by capability. So thank you once again for joining us. We look forward to you joining us for the 4th in the webinar series in the next couple of months. So thank you for all your support. Okay, good morning. Have a nice day.
Thanks.
Thank you.
Thank you all.
Thank you all.